Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe different types of acceleration, and in particular we're going to focus on the Coriolis acceleration for this video. So what we're looking at here is, imagine this road, right? And this road is a bizarre road. Imagine this being like some of the bridges that have that can rotate around. So imagine that this road, this entire road we're looking at, can rotate about this point. And at the instance shown, we have this car with a velocity vector pointing to the right. Right? Now, as far as acceleration is concerned, there's several ways this car can accelerate. Well, one, maybe this guy gives it the gas. If he does, then the rate at which he's moving is going to increase. There's an acceleration associated with that. That's called a tangential acceleration. And that's usually the first type of accelerations that people learn about in physics. Right? However, there's a couple more phenomena to consider. All right, imagine that while this car is driving, this bridge or whatever he's on is also rotating. And you'll notice that the rotation of the bridge is now causing a change in the velocity vector. Now there's actually a couple things going on. Let me take them one at a time. So if this thing's moving, in addition to this velocity, and this velocity would be with respect to the bridge, he would also have a rotational velocity this way. And that rotational velocity, rotation about some sort of center, causes a centripetal acceleration inward. In addition to that, this velocity vector is changing direction due to the rotation. Right? It went from right to kind of up and right. There's a change in direction associated with that. There's an acceleration associated with that, and that's the Coriolis acceleration. Now, one thing to note is that think about that change in velocity. If we look at what the velocity vector did, all right, it went from something like this to something like this. There's a change in velocity that's looking something like this. Now, an important thing to realize, let's talk functionally. What does that change in velocity depend on? Well, the faster the car was moving, in my vector picture, the larger this triangle would be, and therefore the larger that change in speed would be. So that's one factor. This change in speed is going to depend on this, how fast the car is going. It's also going to depend on how fast this is rotating, So you can imagine, as this bridge or whatever it is rotating faster and faster, in this picture, this part of the vector would be larger and larger. So now what we're going to do is we're going to take some time here and actually go through and try to calculate the different types of accelerations, or all types of accelerations we can for this car. All right, so what I'm going to do here is I'm going to get rid of that. And what I'm going to do now is define a coordinate system right at the center of rotation here. Now, I think it was rotating. Let's imagine it's rotating about this point right here. And what I'm going to do is I'm going to put a coordinate system here, an x-axis and a y-axis. Right? X, y. Now, the position vector of the car, we're going to start with that. The position vector of the car can be written as a radius times a vector in this direction. What I'm going to do is I'm going to call this distance right here r. That makes the horizontal distance r cosine theta. That makes this vertical distance r sine theta. So the position vector, we could write r cosine theta I plus r sine theta j. Here's one way we can write that position vector. Now, if I want to know about the velocity vector of the car, then this has to be time differentiated. So the velocity vector is going to equal, now I'm going to go through and time differentiate this. Now remember, the car is moving, so r is increasing. So this term has a time derivative. So we're going to have r dot cosine theta I plus, now this term has to be product ruled. This term has a time derivative. So this is going to be, let's see, in fact, the plus, I'm going to go back and change it to minus r sine theta, theta dot I. The minus is coming from the derivative of cosine being minus sine. The theta dot is coming from the fact that you have to chain rule this. Right, so remember, theta has a time derivative because this thing's rotating. Now the next term would be plus r cosine theta I dot. Now in the way I've set this up, I is a unit vector pointing to the right, and this equation, or I'm sorry, this set of coordinates that I've drawn is fixed, not rotating. So I dot 0 in this example. Had this coordinate system been attached to this to the bridge here and rotating with it, I would have a time derivative. But in the example, or the way I've set this up, it does not. All right, so that term's done. Next term. So now we're going to differentiate this. We're going to have an r dot sine theta j. Next term is going to be plus r cosine theta, theta dot, that's coming from the time derivative of sine theta. Derivative of sine is cosine, but it has to be chain ruled, so cosine theta, theta dot, j. And then again, we would do the third term, r sine theta times the derivative of this, but that thing's not changing. So what we have here is this expression for the velocity. All right, now the point of this video was about accelerations, so I'm going to go ahead and calculate the acceleration now, which is the time derivative of velocity. Now notice I tried to make myself some more room here because I think I got a lot of stuff coming, because look at all these terms. So if we calculate the acceleration directly by time differentiating, we're going to have an r double dot cosine theta I for the first term. That's the derivative of this, hitting that first. Next we have to differentiate this, which is going to be minus sine theta, theta dot. So that next term is going to be minus r dot sine theta, theta dot, I direction. Again, this thing's time derivative is 0, so we'll move on. Minus, right, now we'll move on to this term, r dot sine theta, theta dot, I, plus, whoops, let me go back here, minus actually. Now we're going to time differentiate this, so we're going to have r cosine theta, theta dot. And there's another theta dot, so I'm just going to write that theta dot squared, all right, I. So we've time differentiated this. Here's another term, though, that needs to be time differentiated. So now we're going to have minus r sine theta, theta double dot. Right, that's I. Okay, and we're halfway done. So now we got to differentiate these, and as you notice, I did not have enough room, but that's okay. I'll just keep going. Plus, all right, next term, r double dot sine theta j. All right, that's for the derivative of this, and I'm going to actually, as I get these done here, start underlining them to keep track of what I've done here. So we differentiated to that point. Right now we got to differentiate that, so the next term is going to be plus r dot cosine theta, theta dot, j. Now I've gotten to this term done. Right, now we got to move over to here. Plus r dot cosine theta, theta dot, j. So now we've differentiated this. Next term is going to be minus r sine theta, theta dot for the derivative of this, and there's another theta dot there, so I'm going to go ahead and just square that, j. This is now done. Let's see, plus r cosine theta, theta double dot, j. Okay, simple enough. So there's our expression for the acceleration of that car. Now this is a very general expression. This takes all possible things into account as far as motion in the plane is concerned. Now again, this is still two-dimensional. When these things become three-dimensional, you can imagine it gets quite a bit worse. But this is a two-dimensional problem. So some things to notice. Okay, our double dot terms show up. What, here? Must be another one somewhere. Here. And if we just kind of grouped those together, let's do that. I'm just going to group terms here. So acceleration vector equals. Now I'm going to group it by different types of terms instead of I, J's, and K's. Let me underline these. So I'm going to group, let's see, this term's got an R double dot. Where'd it go? I saw one. Oh, this term's got an R double dot. So what we're going to have here is r double dot cosine theta I plus r double dot sine theta j. Now, if you remember when we were studying cylindrical motion, the unit vector r is in this direction, and that unit vector is equal to cosine theta I plus sine theta j. So this term right here, this is r double dot in the r hat direction is what that term is right there. And I'm going to go ahead and keep that underlined in red. So that's the acceleration that we're getting in this direction if the guy were giving it the gas. All right, next term. So I'm gonna go ahead and use blue here. So let's see. I'm gonna look for terms that look like r dot theta dots. Or I'm sorry, not yet. Let me do the theta dot squared terms. All right, so here's something with a theta dot squared. Here's something with a theta dot squared. I think that's all I see. So we're going to have minus r cosine theta, theta dot squared I, minus r sine theta, theta dot squared j. And again, that was a sine theta. Now I'm going to underline this in blue. These are all kind of what I would call common terms here because they got theta dots. If you look at this carefully, you can write this term. You can factor out the r theta dot squared, and you're left with minus cosine theta I minus sine theta j. Well, minus cosine theta I minus sine theta j is minus r hat direction. So this term that we're looking at in blue here is equal to r theta dot squared minus r hat direction. Right? That's the centripetal term from the rotation of the car. All right, now green. Now I'm looking for terms with r dot theta dots. Oh boy, it looks like there's all kinds of them. Let's see, here's one. R dot theta dot, here's one. Oh, I'm sorry. Let me back up. Again, I want to do the Coriolis term last. Now I'm going to do r theta double dot terms. I'm going to look around here. Okay, r theta double dot. There's an r theta double dot. So I'm grouping those terms together now. Let's see, those were in green. So minus r sine theta, theta double dot I. And again, another green. Plus r cosine theta, theta double dot j. Again, let me underline those in green. R theta double dot is the tangential acceleration you would get if the rate of rotation here is changing. And the minus r sine theta I plus r cosine theta j is giving the what we would call before the theta hat direction. So this term right here, if I write it out, and I'll go ahead and write it in green, is equal to r double dot, and then the direction, if you take minus I sine theta plus j cosine theta, that is giving you what we would call the theta hat direction here. If you remember from cylindrical. All right, next terms. Now I'm going to look at the r dot theta dot terms finally, and I'm kind of running out of colors here. Let's do those in purple. So we've got an r dot theta dot there, and r dot theta dot there, and r dot theta dot there. A little bizarre. I'm expecting maybe one more. Well, looks like I might have missed a term here. I'm gonna take a look at what I got here, write this term out, and then go back and look. I was expecting 4 terms total there. All right, so the next term, let's see. And again, now I need to kind of pick this up down here. So, all right, so the next guy here, purples. Now you'll notice these are like terms here, including the unit vector. So I'm going to go ahead and just add those together. Minus 2 r dot theta dot sine theta I. There's those terms. Plus I'm expecting another one of these terms. Oh, and I look over there. There it is right there. R cosine theta theta dot. All right, so there's two of these terms as well. R cosine theta theta dot, R cosine theta theta dot, J, J. So those add to 2 R dot theta dot cosine theta J. And that purple term right there, whoops, where did it go here? That right there is the Coriolis acceleration, right? So the Coriolis acceleration is coming from these four terms right here, mathematically, when we add them together. Now, let's talk unit vectors. When we take a look at this, we could write this term here can be written r dot theta dot, 2 r dot theta dot, and then minus sine theta I plus cosine theta j is again giving that theta hat direction, right? And if you're wondering why, go back and just review unit vectors and look at the relationship between the i's, j's, and the r's and thetas. And this term right here is the Coriolis term. That's the term that's happening because of the rotation rate coupled with the fact that we have a velocity as this thing's moving off to the right. And again, you'll notice it depends on the speed, like how fast that guy's moving with respect to the bridge, and the rotation rate. It's in the theta hat direction. This, written in the language of vectors, is, I believe it's twice omega cross v, where that would be 2, let's see, angular velocity crossed with your velocity vector. Let me just double check that. So in this example, the angular velocity vector would be plus k direction. If you use your right hand, cross it with that velocity vector direction-wise, that does give you an acceleration in that direction. That's your Coriolis acceleration. So again, the point of this video is to talk about the different types of acceleration that can occur. Let me kind of overview this again. So imagine this thing's rotating, and conceivably the rate of rotation changing. I went ahead and did this fairly generally to take all things into account. Here's a velocity, like the guy's moving along this path, but perhaps giving it the gas. So this velocity vector would be changing. So when we talk about all the different types of acceleration, right, when we look at this instance shown, if this fellow's giving it the gas, there'd be a tangential acceleration that direction. If he were braking, there'd be a tangential acceleration that direction. As far as within the work and math here, that's these terms right here. Boom, this one in red. The r double dot is, positive if he's giving it the gas, negative if he's braking. The I cosine theta, j sine theta gives the direction. That's radially outward. Or if we just leave it like this, it's I, j, k directions. Right? If this thing's rotating at the instant shown, there's a velocity vector this way due to the rotation rate. That's going to give us a centripetal acceleration inward. Within all this work that I did here, that's this term right here. And again, the inward, when you do the cosine theta minus cosine theta I minus sine theta j, there's your minus r hat direction. So we've got our centripetal term. What else do we got? Oh, if the rotation rate is increasing, meaning that if the angular velocity is increasing, we have an angular acceleration, or a theta double dot. That gives us a tangential acceleration this direction, picture shown, right? That's our term in green. R double dot, theta hat direction. And last but not least, this thing is rotating, therefore the velocity vector of the car on the bridge here as it rotates is changing in direction. And notice, like a second later, the velocity vector is going to be like this. So you got a change in velocity that's something like this. Kind of a crummy picture. That's your Coriolis acceleration, and that's the terms in purple. Also notice you can develop these expressions right from first principles, like I always push. What did I do? Started by writing out a position vector. And I just did it in Cartesian coordinates. Time differentiate it. You get a expression for the velocity vector. Time differentiate that, you get this big dog expression, or fairly long expression here for the acceleration. It's long because there's three types of accelerations occurring, and they're in the plane here, so they're not in the directions I and j that I've chosen. And if you think that seems long, you should see, when you make this a 3D problem. So imagine not only is this rotating, but maybe this object here is part of another system that maybe looks like this, that's rotating in a different direction, and then it gets, these terms get really long. But anyway, hope this video helps with recognizing, conceptually the different types of accelerations and how they're calculated. Have a great day.